the Society of Petroleum Engineers, Applying the Best Technologies in Extremely Sensitive Environments workshop.
Buenos dias and good morning, ladies and gentlemen. On behalf of Weatherford, we're very excited and pleased to be part of this very important SPE workshop today. We appreciate you having us. Today my topic will be discussing the advanced directional drilling technology and how it is applicable to extremely sensitive environments. What I'd like to do with this presentation is basically to give you a walkthrough on the process that it takes to drill such a project from the beginning to the end of the actual drilling process. I found in a lot of presentations that I've seen in the past that I get a lot of good information, but it's very fragmented. I get bits and pieces, and it's a bit difficult for me to see the big picture. So I hope from this presentation that you see the big picture, you understand the complications that are involved, as well as the technologies to make the project a success. The agenda today will start with an introduction, followed by looking at the process. We'll start, of course, looking from the preliminary well research on through to the execution and monitoring. And then finally, we'll have a summary and answer any questions that you may have. This is going to be a lot of information to crunch into 20 minutes, so if there's anything you would like to learn more about after this conference, I'd be happy to see you and discuss further. Most oil and gas companies and service companies alike have something in their policy statement to conduct operations with minimal risks to both personnel and the environment. We try to make it part of our policy to equip our employees with the right tools so that they understand the rules and regulations that govern the countries they work in and the environments they work in. Not only what they do through their work, but also how they do it with their daily lives. But one thing that we cannot ignore is the fact that even with these tools, the rig still does create a rather large footprint. This footprint, of course, can be reduced, but it takes looking into such things as the reduction of the physical size of the footprint itself. This can be done by reducing the rig size and the infrastructure that you're using on the surface. But of course, with the technology today, demands are to go deeper and longer, so this is always a challenge that we're still overcoming. Access road alternatives are being looked at, ways that we can avoid soil disruption and wildlife fragmentation. Air emission studies are being conducted to reduce the CO2 emitted into the environment. I want to point in on this point here with the CO2 because it's important to know that when people think of rig footprint or environmental footprint, they can't just think of the actual process that's being done, the equipment that's being used, the physical things that are tied into it, but we have to also think about the time that we spend on the actual project. Air emissions, for example, are time sensitive. The longer we spend on the project, the more emissions we put into the atmosphere. So just something that a lot of people fail to realize is the time involved. And finally, waste management. We're working together as an industry. Every year we come out with some new technology to try to contain the waste management and, for example, treating the drilling fluid so that it's not harmful to the environment and to the people that are handling it. Most, or I should say many, of our locations are quite desolate. There is very little concern about wildlife fragmentation because there is none. Also things such as noise pollution don't really come into play. But when we're thinking about extremely sensitive environments and we want to tap into the reserves below that environment, the challenges that we face, such as endangered species, rare plants or vegetation that rely on a very sensitive ecosystem, or even indigenous people that have had very little or no contact to the outside world and nor do they care to. These are the intangible things we have to think about when we're going to tap into that reservoir, so we have to ask our questions, how? So this poses the question, how do we get here when we have to deal with this sensitive environment above? Well, perhaps the best thing that we can do is maybe take a step away from the environment altogether and approach the challenge from a different angle. That reduces substantially the footprint that we put above the reservoir, but what it increases, of course, is the technical challenges that are required to be able to drill one of these long, extended wells. So what I'm going to do now is step through the process of what it takes to drill one of these wells so that you can see it from the beginning to the end and get the big picture. Weatherford's advanced directional drilling process is in 4 steps. We start off with the preliminary well research. This is basically finding out everything that we can about the formation that we're going to drill into. And then we take that information, use it into how we design the well. Then we move on to the BHA design to decide what we need to put into that well to successfully reach the total depth. And finally, execute and monitor. How we do this with drilling process, drilling practices, and ensuring safety for both personnel and the environment. So we're going to just walk through these steps individually, starting off with the preliminary well research. Geomechanics can tell us a lot about what we're going to be drilling into, looking at the tectonics of the formation, the horizontal stresses that apply. We can learn a lot about what angle of approach we need to take when we go into the reservoir, as well as what direction. Pore pressure prediction. We ultimately would like to optimize our hydraulics. So that requires us to run up to the max or just below the max limit that we can without compromising the pore pressure. So having a good pore pressure prediction is essential for maximizing hydraulics. Wellbore stability workflow. Being able to recognize the things that we can and can't control, take the things that we can't control out of the equation, you can't control Mother Nature, and just center in on the things that you can control and try to find a good process that works to mitigate those problems and see them through. Well trajectory analysis. Again, back to how we're approaching the formation that we want to drill into, the type of stresses that are involved on that. What do we need to think about when it comes to drilling fluid? Hole stability issues, of course, which Latin America has quite a bit of. Casing point selection. How many casing strings are we going to run? What hole sizes do we need? What is the optimal hole size that we should use in the horizontal in order to keep the cuttings moving and up and out of the hole? And finally, hole collapse analysis. This is basically looking at what are the maximum limits that are required to collapse the hole, and then working within those limits by a safety factor. So once we have all this information, which is very good, we've done a lot of research on it and we're ready to now apply it, we move it into the well design. The well design is a very critical part. I would say of the 4 points that we have up here through the process, your well design and your execution monitoring are probably the top 2 to spend the most time and energy with. If you have an improper well design, you can ruin your entire job. You're going to have to live with that mistake from the beginning till you get to the reservoir. And believe me, if you get it wrong, it can make your life very difficult. Traditionally, in the rigs that are drilled with shallow wells, build and hold is an acceptable assembly. But historically, we found more success with build and drops, double builds, and even catenary wells. Things to think about when you're doing this is how long do you want to stay in the reservoir? Once you get into it, at what angle do you want to approach for hole stability issues that we talked about in geomechanics, as well as what angle do you need to be able to optimize your hydraulics to keep the cuttings moving up and out of the hole. This is down to your dynamics of fluids, of course. So once you have your well design chosen, you move on to actually putting that well design into your well planning software. This can give you valuable information to what limits you need to have for your BHA, for example, what dog legs that you need to create in order to complete the well. This also gives you good information as to anti-collision, and I'd like to hone in on this part real quick about looking at things as a project management view for the whole project, not just one individual well. Perhaps a lot of information that you've perceived is that we do things one well at a time, and that's just not the case. If you're doing a project that involves 10, 15, 20 wells, you look at all those wells on the project from that pad and you ensure that the relationship between each well is a stable relationship. If you have a very easy well, even 9 easy wells and 1 difficult well, that 1 difficult well will catch you at the end. So what we try to do is ensure that even if we have to make some of the easier wells a little bit more difficult to bring the difficult well down to an acceptable level, then we go ahead and do that for the safety and for the compromising the whole project and thinking about that. Torque and drag and hydraulics. After we're finished with getting our well trajectory, we move it into the torque and drag and hydraulics software so that we could determine very important things, especially on an extended well, that we have to live with, which is, of course, the amount of drag that you're receiving from your drill stem. Because you're going out so long in a horizontal with many miles of pipe, you basically have all that sitting on the well bore, and you're trying to push it through to get to TD. So drag becomes quite an issue, as well as torque. Being able to turn that pipe with all the reactive torque and the torque power that you need on surface to be able to get the bit to move. Hydraulics, of course, moving cuttings up and out of the hole are always important as well. One thing to note about the torque and drag is we can identify such things as sinusoidal or helical buckling that can occur in a well bore. So if you're, say, going through and you're at your kickoff point and your landing point, which is where these typically occur, your pipe can buckle in kind of a snake profile, or even helical, which is where it bends down on itself, and that basically reduces your bit from moving forward, and you're stuck. You have to basically redesign the BHA. So what we try to do is identify that up front with the software so we can avoid it at the rig site real time. It will take well design to reduce that and to ensure that the dog legs are low enough so you don't incur any buckling. But in the case that you can't reduce it anymore and you're at your max with the well design, you can always move interchangeably between these two, going to the BHA design to help mitigate those areas, those trouble areas. Ways to do that would be, for example, to roll the pipe through rather than drag it. And we'll talk about that later in the BHA design. So now that you've got your well design, it's time to put tools in the hole. For directional drilling, only have one real tool of choice to drill this type of project, and of course that's the rotary steerable system. Rotary steerable gives you true 3D drilling. It allows you to move an inclination up and down as well as directionally without having to pull out a hole and change BHA. Gives you continuous rotation, so in 2 points there you can rotate continuously to move the cuttings to the upper side of the borehole, which is where the higher angular velocity is, to shoot the cuttings down the conveyor belt. It also allows you to have a smooth wellbore path, so you don't have any ledges that you would typically have with a mud motor. Ledges are points of hanging up as well as additional friction, which you can't live with because you've already got so much pipe out in the hole, you've got enough friction to deal with already. And of course, no sliding, as you would with the mud motor. Sliding takes time, as you all might know. You have to pick up, orient, get your slide in, especially with as much reactive torque that you're dealing with on these long wells. It's just not possible. But you can see here with the profile of sliding, with the slide drill, it creates what we call tortuosity in the wellbore. And that's what we were talking about with the additional friction that's applied. Rotary steerable systems can be used in a conjunction of different BHA configurations. A popular one is to mount it with a mud motor above it. This allows the mud motor then to turn the rotary steerable faster, which gives you a faster bit speed, so you can cut the formation more quickly. I'm going to divert to our K&M guys with a very good point that they made is it's not all about speed, it's about optimizing. And if you're drilling so fast that you overload your hole with cuttings and you're not properly moving it out or creating a smooth level of cutting beds, you're going to wind up having yourself some problems there. So the key is to drill as optimal as possible. Just a couple quick examples of rotary steerable in action. This is one that set a footage run in the Eagle Ford. It was a 11,900 foot single run. Started off in the vertical at 5,600, basically kicked off, built the curve at 8 degrees per 100 foot, and then drilled the lateral to 16,559. The value to the client, of course, was 75% increase in ROP from the conventional mud motor assembly. It was the fastest well drilled in the Eagle Ford, winning the client $700,000 ahead of AFE. So again, driving home the point that this is a faster system, it's more efficient, it saves money, it saves NPT, and it saves that time that we were talking about earlier with the emissions to the environment and our footprint, how long that footprint remains on the project. So something to think about there.
5 minutes more.
Another quick example, over 13,000 feet in a single run. This was a record that we set in the U.S. It saved 2 runs ahead of the associated costs. This was, again, was a build. This actually was a vertical built to 8.5 degree. They kicked off at 8 degree per 100 foot build and turn, and then they continued the lateral for 7,200 feet to TD of 14,000. This was a 7-day run, single run. That's the great thing about the rotary steerable, is that you're not tripping out and changing BHAs to be able to make your build and your lateral, etc. It saved 2 days off the drilling operations, again, ahead of AFE. And they were able to get the casing run to bottom with no problems, so there's no ledges or tortuosity they have to deal with to run the casing. Next, we move on to the formation evaluation tools we'd select. This is the MLWD. You have quite a suite to pick from with most service companies, and the main thing I'd like to drive home here is to ensure that you have some type of bore and annular pressure sensor. Because the LWD is in the BHA, it's on the biggest collars that would be on the drill stem, and having an annular pressure sensor there is key so that you can ensure cuttings, transport, and monitoring those, as well as monitoring your ECD. Drilling tools is the last thing that we're going to add to our BHA if needed. As we were talking on the well design phase, when you're dealing with sinusoidal helical buckling issues, you could mitigate some of those areas by adding rollers, torque and drag reducers that can help you roll that pipe through that trouble spot rather than drag it through and have that high buckling point. Also, we have the case of hydraulics. If we need to improve the hydraulics, we always have under-reamers that we could default to. The BHA analysis, finally, is conducted with the BHA that you finalize for the project. Basically, you run the BHA analysis. It's a software-based program to see how that BHA will react in the well design that you chose. You could find out a lot about the contact forces of that BHA, the type of stress that you're going to be looking at, and the vibration that will be incurring on the MLWD package that's in hole. No one wants to be able to drill in hole, drill as fast as they can, and then have an MLWD failure that they got to trip right out of hole to change the BHA. So we try to make sure that we cover all the bases, including keeping the integrity of our drilling package intact. Finally, on the execution and monitoring stage, we have the drilling, optimization, and real-time operations centers. Again, this is the second most important part of this phase process. The drilling optimization is key because it brings in project management, experts that have extensive knowledge on drilling with extended wells. They can sit in a room with other colleagues and watch the well, both at the client's office, on site, and from one of the RTOC centers. And it really helps for them to monitor the best practices that are being used and to be able to avoid train wreck situations from happening. This is valuable, of course, both to the safety of the personnel and to the environment. I'm just going to show you a real quick example here of how that action can happen. This is a well that they're tripping in. This is measured depth here on the bottom and hook load on the vertical. And as you can see, they're just tripping in hole. They finished TDing the well, came out of hole. Now they're running in for clean out or wiper trip. They run in, everything's fine. They're running on the friction factor line, and then they get to the liner hanger. Suddenly they start having problems. They got to work the pipe up and down. This is an indication of a cuttings buildup at the liner hanger. So when they TD'd the well and they pulled out, those cuttings were dragged back up to the liner hanger, and now they got to fight their way through it. Now we get out into the open hole, and you can see the amount of drag that's building and the amount of tight spots that we're having to work through. These are cuttings beds that's built up that need to get cleaned and smoothed out so we can get this production string to the bottom. Pulling out a hole, you can see how much drag now has been increased. on the drill stem. Another indication of a lot of cuttings that are pulling back the stem from coming out of the hole smoothly. So at this point, we know that we have to do another clean-out run, basically to get all the cuttings moved to the bottom of the hole. If you're not monitoring this, and you just let this go blindly, and you just rely on the driller to trip out a hole without even knowing what he's looking at, you're going to be running that casing string in the hole, and you're going to wind up having a big problem, possibly stuck pipe that you might be fishing out for 2 weeks. So something to think about. Pulling up to liner hanger, of course the the cuttings drop off here, pulling back out of hole, no problem. That concludes the phase process. I'll just run through a quick recap, starting with the preliminary well research. We talked about the geomechanics, how that's used to identify the formation that we're going to drill into, pore pressure prediction, etc. Gather as much information that we can to use into our well design to decide how best to drill the well and to ensure that we have the lowest torque and drag and the most optimal hydraulics. Use BHA design to design what you're going to put into that well to be able to successfully get to TD of that well design. And finally, execution and monitoring to observe the drilling process and ensure the integrity of the hole and the safety of the personnel and the environment. At this point, I'd like to say thank you for allowing me to present to you today. I hope this gives you a bigger idea of the whole process that's involved, although I didn't get into as much detail on any aspect, but if you'd like to talk more about it afterwards, I'd be more than willing to share that with you. Thank you.
Thank you.
The Society of Petroleum Engineers, Applying the Best Technologies in Extremely Sensitive Environments workshop.